Alright, so let's watch Applications of the Derivative 2.4.
All right. Our day today is all about the applications of the derivative, and just a few of them. I mean, it's so far-reaching, I can't give you everything. But I'm going to give you a few that I think are kind of interesting. So we're going to talk right now about applications. We're on section 2.4. We're spent only a little bit of time here. Firstly, let's say that you were in the process of selling something, and for instance, for DVD sales, you ever watch like DVD sales when they first come out, like after, or I guess it's Blu-ray now. When they first come out, people go and they buy a whole bunch of them, right? But then like 10 years down the road, are you still buying that DVD with as much enthusiasm or are people still buying it with as much enthusiasm as they were 10 years previous? Probably not. For instance, Transformers. When Transformers came out on DVD and Blu-ray, people bought it up, right? Because it's a great, I like it. I'm a math guy, but I love that movie. And now, I mean, you can find it all over the place, like $5 movie bin, right? I mean, you can find it anywhere, so people don't really buy it as often because most people have it already. Well, if you're going to buy it, most people already have that. Unless you're cheap like me and you just wait 10 years and they go in a $5 bin. That's me, I do that. But most of the times, DVD sales drop off, and they usually drop off pretty rapidly. Here is actually a model of how DVD sales work. So for this particular DVD. So DVD sales. The sales in terms of T years is this. Tell me a couple things about T. First, I'll tell you that T is in years. T equals years. Tell me something else about T. Why is T positive? Because you can't go backwards in time. That'd be awesome, but no, we can't. We don't have a time machine. Calculus doesn't make time machines. It might be
Approach
able
is zero.
but we don't have a time machine for calculus. So no, T has got to be greater than or equal to 0. Which hopefully makes sense. I mean, if you plug in a 0 up there, 7 times 0 is 0, right? Over 1 gives you 0. That means at the moment that you start selling them, you haven't sold any yet. Then every T after that, you're going to get the number of sales. I think this is, I don't know, maybe millions or whatever they say. So this is our model for the number of DVD sales after T years. We want to find a couple things about this, 3 things namely. First, I want to find the rate of change for the sales. Rate of change for sales. Number 2, I want to find out when the sales are going to peak. That's probably important to know, isn't it? If you're going to be a person selling DVDs or whatever you're selling, you want to find out when your sales are going to peak. You want to find out when sales are going to fall, how fast they're going to peak, how fast they're going to fall. That's probably important stuff. When will sales peak? And how fast are sales increasing right when the movie's released? This is an interesting question. So, number 1.
Okay. Well, I guess I'll just find the derivative first. So plug this into the, or do we want to do that? 7t over t squared plus, no. Yeah, definitely plug this into the, it's called the quotient rule. Be slow at doing this because I haven't done this since yesterday. Okay. So t squared plus 1. The derivative of this is 7. I guess this would be with respect to t, wouldn't it? Not x. So this is just 7 minus 7t times, let's see, I'll put brackets around this. This would be 2t all over t squared plus 1, I forgot to square it. This would be in parentheses, this whole term. Seven t squared plus 7 minus 14t squared. I'll probably FOIL this. Negative 7t squared plus 7 t to the power 4 plus t squared plus, so plus 2t squared plus 1. No, actually I don't like that form. And this should be about it. Rate of change. When will the cells peak? I don't know how to figure that out besides just plugging in numbers, so. Negative 7 plus 7. Yeah, I'm not too sure on this one actually. I'm gonna watch this explanation on this.
Find the rate of change for sales. Number 2, when will the sales peak? Number 3, how fast will the sales increase right when we release that movie? That's what we want to know, and it's going to be modeled by this curve, this function. So, hey, let's talk about rate of change. Have we talked about rate of change in this class before?
Yeah.
Sure. What is a rate of change?
Slope.
It's a slope. What's a slope for us in calculus, in terms of calculus?
Derivative.
So can you find the derivative of that? Go ahead, get started, go for it. What will you have to do to take this derivative? That's definitely quotient rule. Hopefully you practice that on your homework with the quotient rule. So do the quotient rule. So the derivative of the sales will give you the rate of change for sales. Little note in your notation. You can't write ddx here.
Yeah, SB2.
What do you have to write?
DDT.
Because your variable is t, ddt.
Have it?
It is habit. No, it really is, because I'm used to writing DD. I actually did that mistake a little while ago. You're all looking down, so you didn't catch it. I was like, oh, cool, I didn't see it. But I wrote DDX because it's such a habit to do. But be careful on what your variable actually is. The function is S, yes, but the variable is t. So DDT says with respect to t, low D high minus high D low. Square the bottom, and you're all good. So, did you make it that far, folks? Good. So quotient rule should probably be like embedded, like tattooed on your brain at this point, along with the product rule. Those rules aren't the hard part, honestly. Doing this is pretty easy. And the little derivatives are actually pretty easy. It's the algebra afterwards that could be kind of tricky. So here we're going to go ahead and derivative of this, no. Derivative of this, yes. So we're going to get 7t squared plus 1, I'll put the 7 out front, minus 7t times 2t, t squared plus 1 squared. Are you okay with that so far? Sure? All right. Well, if we distribute, we're going to get 7t squared plus 7 minus 14t squared all over t squared plus 1 squared. Still okay so far? Basic algebra. If we combine some like terms even further, we'll get our actual derivative. 7 minus
Looking good so far.
7t squared over t squared plus 1 squared.
I probably wouldn't want to plug that into the rate of change to find when the sales will peak, huh? I don't know though. Maybe he's gonna plug like 1, 2, 3, 4 into the original function. Cause that would, I feel like that'd be more accurate.
Are you okay with that so far? All right. How many people feel all right in getting down that far? Now, I don't think you can simplify it. If you do factor out the 7, you get 1 minus t squared.
Before you got to factor out a negative 7.
You factor out a negative 7, you get t squared minus 1.
Oh, okay.
But that still will not simplify at all. Okay, so that's as far as you can make it there. You sure you're okay so far? So what's the rate of change of DVD sales? It's right here on the board. That's the rate of change. So this tells you for any time how your sales are increasing or decreasing. How many people understand that? Feel okay with that derivative? How your sales are, that's the rate of change. So this tells you for any time how your sales are increasing or decreasing.
Oh, okay.
How many people understand that? Feel okay with that derivative? Yes, no? That derivative is the rate of change. It's saying how fast you are climbing or falling with your DVD sales. Now, the question is, when will the sales peak?
So, let me see if I can figure that out. So this would be S1. 7/2. S of 2. (14/5). S of 3. 7/3. 3 squared plus 1. Four. (28/17). So 5. There's gotta be a better way to do this. There's no way. 35/26. S of 6. (42/37). (49 plus 1). Alright. And then you have to like, I'll plug all these in, find the decimal form. That should tell me the peak. 3.5. 2.8. Oh, I guess you don't have to go much further than year 1, huh? Sales peak in the first year. I mean, that was kind of obvious, I guess. But yeah, so. I wonder how he's going to do that, though. And then the last question, how fast will sales increase when the movie is released? Oh wait, that's easy. You just plug in 1 to the derivative, right? (-7, 1 squared plus 7). Plus 1 squared (-7 plus 7 over 1 plus 2 0 0. What's that tell me? It's kind of useless. Wonder why it does that. Alright, I'll just watch the rest of the video then.
When will
So it says the rate of change is 0 for year 1. Very
sales
strange.
peak? Can you tell me what happens at a peak? What happens?
It's when the value is the biggest before it starts to fall.
Why? Yeah, sure, because peaks go, I'm climbing, I'm climbing, I'm climbing, I'm climbing, I'm falling, I'm falling, I'm falling, but right here between increasing.
But you can't find that because it's a sharp point. Oh. That's why it was 0, because it's a sharp
And
point.
decreasing, something has to happen. The slope has to change from positive to negative. If the slope changes from positive to negative and it's a continuous function, well, that right there was that intermediate value theorem, or was it Rolle's theorem or something like that we use? It says if you're going from positive to negative and it's continuous,
Can't find the derivative.
you have to be crossing over 0 at some point, don't you? So we have to hit a slope of 0. So that means that at our peak, we're going to have a horizontal tangent line, or the slope will be 0. So when will the slope peak, or when will sales peak? When our tangent line is 0. Or when the slope of the tangent line is 0. Well, hey, look. That's the slope of your tangent line. True? That is your slope. What do we need to do to find out when the sales will peak? What do we do with this piece? Great, yeah. If this is our slope, and we
Wait, can you find it? And it's a 0? But it's a sharp point, isn't it?
know we're going to peak when the slope. Well, hey, look. That's the slope of your tangent line. True? That is your.
Okay. So set this equal to 0. Negative 7t squared plus 7 for t squared plus 1. Plus 7. Negative 7 equals negative 7t squared. Negative 7 over negative 7 is 1. T squared equals 1. T equals plus or minus 1. So what are we finding again? How fast will sales increase when movies release? Guess well, it'd have to be plus 1. Increasing with the rate of change of 1, I guess.
Slope. What do we need to do to find out when the sales will peak? What do we do with this piece? Great, yeah. If this is our slope, and we know we're going to peak when the slope is 0, let's set this thing equal to 0, and then we're going to solve it. Nod your head if you're okay with that idea. Are you sure you're okay with that? Okay, good. So we're going to say the tangent has a slope of 0, or the slope function.
Still confused on that sharp point thing though.
Equals 0. Now that might look a little bit daunting, right? So, oh my gosh, that is a rational function. It's equal to 0. What in the world do we do? What do we do? Well, let me say this. Is it possible for you to have the denominator equal to 0? No, not really. Because if it is, it's undefined. You're not going to have that. So really, the only place where this will equal 0 is where the numerator equals 0. In fact, you can see that. Multiply both sides by this expression, you still have 0 on the left-hand side. You see it? So this is kind of actually really nice. We don't care about this piece so much. We care about where the numerator is equal to 0. That's something we can work with. How do you work with that? What would you do? Solve it. Solve it. Come on. How do you solve that?
Factor out negative.
Okay, you could factor out a -7. We did that over here. That's fine. You could add 7t squared to both sides, divide by 7, and take a square root. You could do that. Either case, you're going to come up with 2 answers. Do you see your 2 answers? What are they? Plus and minus 1. Very good. So I'll do it by the adding 7t squared to both sides. So if I add 7t squared, 7 equals 7t squared. Well, if you divide by 7, you're going to get t squared equals 1. Which means that t equals plus or minus 1. T equals plus or minus 1. Show of hands, how many people feel okay with getting plus or minus 1? Good for you. Okay, so we're just solving our equation. It's quadratic. You know, you can solve it a couple different ways. If you don't have that middle t term, take a square root. That's probably the easiest, or factor it. Either way, you get +1 and -1 no matter what. Now, explain to me which one of these works and which one of these doesn't work.
+1 because it's when the sales peak. No, that's not a good way of explaining it. Dang it, man, I don't know how to prove this. I know it's +1, it has to be.
Positive 1 more.
1 works. +1 works. Why doesn't -1 work? We already defined t, right? That's outside our domain. So
Oh,
this
okay.
one, we're going to say, no, that would be a year ago. We released the movie, and a year ago it peaked. Haha, that's the worst business plan in the world. Okay, no, you made no money.
Oh, this is saying sales peak at 1 year, okay.
Makes sense.
Easy.
So, okay, we have, it's going to peak after exactly 1 year. So you want to have the most DVDs available in 1 year from when you release your date. Does that make sense? You also probably expect the biggest profit at that point because people are going to be wanting it. You can have the price still way jacked up, and people still buy it. Supply and demand, right? They really want it. They're increasing. Okay, great. Now the last question, how fast are the sales increasing when the movie is released? When is the movie released? At t equals what?
0.
Yeah. Yeah, that's an interesting question. Even though we haven't sold any yet, we want to find out how fast we're going to be increasing our sales. That's weird because we can do that at t equals 0 with our derivative. So this happens when t equals 0.
Seven.
How fast will sales increase when the movie is released? How fast, that relates back to our rate of change. So we've already found the rate of change. This is how fast you're climbing or how fast you're falling. You understand that you're slow. This is how fast you're doing something. So if this is how fast, and we're asking how fast when t is 0, what do you need to do to figure that question out? Plug in 0. Yeah, plug in 0. So we actually want to find s prime of 0 for this. That will be 7 minus 7 times 0 squared all over whatever that is. How much is that going to be ultimately when you get done? 7. 7 or negative 7? 7. So it's climbing. It says positive 7. And what I'm guessing is this probably is in millions of DVD sales per year. So at this time, their rate is you're increasing at 7 million DVD sales per year. Now, is that a constant? No. This is not linear. So in the next moment of time, it's going to be a little bit different. Okay, at t equals 1, it will be at t equals 1, it's going to be 0, right? If you plug in 1 here, you get 0. That's how we got the 1. So it's going to be 0. So the slope is probably, I'm not sure for sure, but the slope is probably decreasing up until that point, and continues to decrease negatively as your sales fall off. But so right at the moment when you release it, well, that's when you're going to have the most amount of the quickest sales, the quickest. So you say, okay, we're selling the most per time. When are they going to peak? Well, they're going to peak after a year. After that, they're going to fall off. Okay. Does that make sense to you? Now, there's a couple of things that we have talked about before. I just want to refresh your memory on these. They shouldn't be really anything that you're having to learn new, except for maybe one of them where we talk about marginal cost, which is a really interesting idea. We'll talk about that, but basically this is just integrating, well, not integrating, but combining our idea of a derivative with some of these applications.
I wonder what would happen if the...
Were there any questions? Hope not.
What if there's multiple like sharp points, or where it peaks and like increases, decreases, increases, decreases? Like, how would you find? Maybe it would give you a bunch of different answers, like how it gave +1, -1. It'd give you like a bunch of those. I'm not sure.
I know.
Just a couple ideas here. Squeaky pen. If I give you a position curve, what happens when I take a derivative of my position curve with respect to t? What do I get out of a position curve when I take a derivative? Do you remember?
Instantaneous velocity?
No, not acceleration, but you're close.
Velocity.
You get velocity. Remember that the derivative is a rate of change, right? Rate of change will be a velocity. That's the velocity of DVD sales, how fast they're climbing or falling. That's what that says to you. So if I take a derivative of my position curve with respect to t, we've already talked about this before, this is a velocity. So how you find a velocity is by taking a derivative with respect to t, the first derivative. So this is velocity. The next question is, what would happen if I take another derivative? So for instance, let's say, and by the way, you can represent this as s prime of t. That might be a little bit more concise than this ds dt. So we'll do that, and we'll stick with that. Take a derivative of position, you get velocity. What would happen if I took a derivative of velocity? What would happen? This is the, if you think about this,
Acceleration.
this is the rate of change of the rate of change, or in other words, how the velocity is changing. How the velocity is changing. That's acceleration, that's right. So if you step on your gas pedal faster or like heavy, you're accelerating more, right? Your velocity is still changing, but how you're changing is your acceleration. So this derivative of velocity gives you acceleration, which, if you look at it, can you recognize that this is a second derivative of a position function? First derivative is velocity, second derivative is acceleration. If I spelled acceleration right, I'm not a good speller. Is that right? Is this right?
Yeah.
I always do the extra L. I don't know why.
Acceleration just magically appear on the board in the video.
No, I don't believe it's like that. So acceleration, that's a second derivative. It's how the velocity is changing. What about third derivative?
I don't know.
Or the derivative of acceleration. That would be the third derivative of your position. Well, if you think about it, velocity is how your position is changing. Acceleration is how your velocity is changing. This should be how your acceleration is changing.
Yeah, but what is that?
You ever stepped on your gas pedal really hard and have a really nice fast car, and your head goes, right? What happens to your head is called the jerk. Your head jerks, right? Jerk, not me, I'm a jerk. But jerk, as far as this goes, it defines how the acceleration is changing.
Is that actually what it's called?
Is that a technical?
Seriously, jerk.
Really?
Really, really.
Wow.
Jerk. Yes.
Momentum.
Nope, jerk. Velocity is how its position is changing. Acceleration is how velocity is changing. The jerk is how acceleration is changing. If you accelerate and then you change acceleration really quick, you're going to be jerking, aren't you? Yeah. Hope so. 'Cause once you do acceleration once, jerk. You don't jerk again unless you change acceleration. If you have constant acceleration, you go whoop, and then you stick back there for a while until you stop accelerating. And that's a change in acceleration, isn't it? But if you accelerate and then your turbos kick in, like mine, you go brr, bam, and your head goes boom, boom, twice. It's really cool. You should really try it. Get a twin turbo car and you'll have a lot of fun. You'll probably die younger than you should, but you'll have fun. Okay, so velocity, acceleration, jerk. Just a quick example. Let's find acceleration and jerk of this position curve.
Jerk. It's a new one.
We could say this is like the position in
So jerk would be like meters per second cubed then, huh?
t seconds. So this could be seconds here.
S of t 2t cubed minus 15t squared plus 24t find first derivative or velocity. You get 6t squared minus 30t plus 24. Find the second derivative or the acceleration. 12t minus 30. And find the third derivative or the jerk is 12. Yeah.
Find velocity, find acceleration and jerk.
Just acceleration and jerk. It would be, this is acceleration, this is jerk.
Go for it. Find acceleration and jerk. What's it going to take to find acceleration? First, second, third derivative, which one?
For acceleration?
For acceleration.
Second.
What's the first one?
Velocity.
Okay, what's jerk then?
Third.
Okay, so if we find all of these derivatives, I know this one is 6t squared, by the way, on your homework. I passed it out to you, right? Some of you are forgetting your exponents. You're taking stuff like this and giving me 6t. You can't do that. That's going to really affect your problem, especially with acceleration and jerk. And then you take a second derivative, you're way off. So be careful now. Minus 30t plus 24. So far, so good? Yes, no? Okay, so second derivative, this would be the velocity at any given time. Say how fast you're going, plug in a number, you can do that. The acceleration will be the next derivative. How fast are you accelerating at any given time? This is going to be 12t minus 30. You okay with that so far? Lastly, the next derivative, or third derivative, should just be 12. Constant jerk factor. That's me, I'm a constant jerk.
True.
No, I'm just kidding. But if we found acceleration and jerk, we just need to know that this is velocity, this one's acceleration, and that one is the jerk. So acceleration, jerk. It'd be quite uninteresting for me to ask you, so what's the jerk at t equals 3? Because you say
Doesn't matter,
it's
it's always
constant, right? It's
constant.
never changing. So from when we start, you're always jerking around the same rate. It's always a factor of 12, however they want to describe that. Acceleration, though, would be interesting. Could I ask you, what's the acceleration when t equals 3? Could you find that out?
Yep.
So
-4.
acceleration at t equals 3. How would you find it? Yeah, we're going to go back down to this one, s double prime. That is our acceleration. So if we plug in 3, we get 12 times 3 minus 30. Would you say 6? Sure.
Whatever unit.
6 feet per second squared would be acceleration.
Oh wait,
Uh,
it's 36, not 26 again.
This would be feet per second squared, should be feet per second cubed, I think.
Yeah.
Unless I did my units
Probably.
just wrong right now, but I'm pretty sure that's how it should be. I believe. I'll check on that for you. Next up, could I ask you this question? When will velocity be 0, or when will acceleration be 0? Could I ask you those things as well?
Yeah, you could set it equal to 0.
Could you find the time at which those are possible? Let's do acceleration just for the ease of it. But you should be able to tell me when acceleration is 0. If you set this equal to 0, you can say, oh, I'm not really traveling if this works out. You can factor
3
it
divided by
correctly.
12.
Or you the quadratic equation. You should be able to figure out the times at which you're not moving at all, for instance of time. Acceleration, find out when you're not accelerating. Let's try that one. When is acceleration equal to 0? In that case, you take your 12t minus 30, set that equal to 0. When's acceleration equal to 0? If we add 30 and divide by 12, we get what?
5.
So 2.5, right? 5 halves?
Yeah, 5. 2.5 seconds.
2.5 seconds. So at 2.5 seconds, our acceleration is 0. What happens is we either temporarily stop accelerating for a second and continue, or we change our velocity from increasing to decreasing. Something happens with our velocity there, most likely. That's what happens. We'll talk about, or our velocity could change from increasing at an increasing rate to increasing at a decreasing rate. One of those things happen. We're going to get more into what the interplay between first and second derivative in, I think it's chapter 3, where we're actually going to be graphing these using this information. For right now, do you understand the position, then the velocity, then the acceleration, then the jerk? You find those different things about it? Yes or no? Okay. There's only a couple more I really want to talk about. One of them is fireworks because it's so much fun. We can actually find things out about heights of objects that we shoot into the air. So let's talk a real
Fun when they
quick
peak.
example about some fireworks.
Already done that with the movies.
For this particular firework, this is the model of its height.
Whoops.
That would be the pull of gravity. That would be how it's in, the velocity is overtaking its the gravity if it's going to shoot up into the air. By the way, is this shooting off from a height of anything or from the ground? What do you think? Like ground.
There's no if it was from the ground, it would say like, or if it was from a height, it would be like plus 100 feet or something, or whatever value.
Because there's no constant.
There is no constant.
A
If it was like
constant.
plus 500, you know, that'd be kind of cool. We shoot off of a cliff. Or if we had negative 350, it'd be we shoot from under the ground and it shoots up. Probably kill some people, but whatever. If it's pretty. Anyway, can we do a couple things? Firstly, can we find out the maximum height? Can you find the maximum?
Yep. Should be when it peaks, right? We want to set the rate of change equal to 0. Yeah, not this. Because that would just be 0 seconds. Which isn't what we want. So first find the derivative. Negative 32t plus 256. Set that equal to 0. Negative 2. I'll add 32t over. 32t equals 256. 32. 32. T equals 256 divided by 32. 8. It peaks at 8 seconds. Or was it? If he's asking from what height it peaks, then you plug in the 8. And then you find out. I'm gonna do that too. Why not? So it peaks at 8 seconds. You plug that in. So we got negative 16 times 64. Negative 10. What is it, 24? Yeah, 24 plus 256 times 8. 48 minus 10, 20, it's gonna be 1024. But yeah. 1024 feet, I'm guessing, because that's what he usually does for the unit. Peak. Peaks at 8 seconds. Alright.
Why would you want to find out the maximum height of a firework?
How that you shoot an airplane or not.
Or,
You know when to blow it up?
yeah, exactly. Do you want it to go, all right, let's let it, boom, crap, because you're gonna die, you know, and it's not gonna look very cool. It might, but probably not. If you're close enough, it would. But you want to attain maximum height, not come back down and then blow up because you're gonna kill people, but attain maximum height so everyone can see it, and then right as it stops in midair, boom, right? That's what you want to have happen. So this is the model for that. Can we find max height? Sorry for anyone who may have had a firework accident. It's a serious. I can't say it without laughing. That's, seriously though. Have you ever seen a firework accident? They're not pretty. They're not cool. You don't want to do that. Anyway, when is the height going to peak?
When slope is zero.
When what?
Slope is zero.
When the slope is zero, or in other words, when the velocity is zero. Do you understand? Because it's going to climb, right? It's going
Or
to climb,
velocity, yeah.
and that's going to fall. But I can't even catch a pen. That's why I'm a mathlete, not an athlete. But if you toss it, if you toss up a firework or a pen or anything, it's going to increase speed and it's going to decrease speed. But right in between it, it's going to have a velocity zero, isn't it? And that would be the slope, because velocity is a slope. It's a slope of our position curve. So we want to find the maximum height where the velocity equals zero. This happens where the velocity curve equals zero. How do you find the velocity curve?
Find the derivative.
Do it. Why don't you take the derivative, set it equal to zero, and see when your firework is going to reach the maximum height. Remember that velocity equals the first derivative of a position curve, in this case, s. If we're able to find our velocity curve and say, oh, we want to find out when it's zero, when it's changing, and that's most likely going to be when it's changing from increasing to decreasing. Now, if we solve that, you add 32t to both sides. Eight. That's a pretty high firework.
Usually 256 feet per second.
Whatever that is, yeah. So 8 seconds. So you're going to launch it. 1, 2, count to 8, and then you want the fuse to explode. You want to set that fuse for 8 seconds. Any more than that, you're going to be declining. Any less than that, you're still going to be going up. You won't get the maximum effect of that thing. Can we understand the problem here? Okay. Now, something that is kind of cool. We can also use calculus. And if you ever take business calculus, or you take business classes, or marginal economics, or managerial, no, I don't know if it's managerial, but I've had to take that as a business major as well. You can actually apply calculus to business and find out when you should stop producing goods. Because after a while, there's something called marginal cost. It's the cost of producing the next item, and sometimes that goes up. So you produce something, then produce the next one, it's more expensive than the next one. And what you want to do is match that up with your profit, right? You don't want to produce as much as possible, because what if you start losing money after a time? That would suck, wouldn't it? To be making more and more, it costs you more and more and more and more. Ultimately, you're going to cut into your profit, right? So we can talk about, well, I'm not going to get into all that. That would be business, all right, in economics. But I will show you how you can find marginal cost. So here's our cost function. I'll give you the definition of marginal cost too. Marginal cost
$9,000.
it's actually the way that your cost is changing, or the rate of change of your cost. If your cost is going higher or going lower, that would be your rate of change of that. So, and that's marginal. It's the cost of producing an additional item. So if you produce 200, what's the cost to produce 201? What's the cost to produce 202? The marginal is the next. So marginal cost would be the cost of the next item. Do you understand the idea of that? It's going to be changing, right? Because this is a changing curve. So this thing, let's see, what is that, upside down parabola there. So your cost is going to be changing after a certain point. At this one, it looks like it's going to peak. Your cost is going to peak and then go down. At least that's what I'm interpreting that as. So your marginal cost is the cost of producing an additional item. And it's the rate of change of your cost. So that means it's the first derivative.
So if you want to find out where it peaks, I guess when you're, what would it be? If you when the cost peaks or your profit? Cost of producing additional item, rate of change of cost. Well, okay, I think I'm finding the rate of change of cost here. So negative 2.2x plus 200 set it equal to 0 to find the peak. Negative 2.2x equals 200. 2.2 x equals 90.9091. And this would be the, I'm not sure if this would be the most expensive or the cheapest. Yeah, I'll have to see what he says in the video.
Firstly, here's an interesting question. What's it cost to produce 0 items?
$9,000.
How much? It doesn't cost 0. Plug in 0. X is your number of items. Plug in 0. How much you got? Why would it cost you $9,000, let's say dollars, to produce nothing?
Equipment and everything.
Yeah, you have overhead, don't you? You have rental. You have people. You pay them whether they sit
all
there
that,
on
I guess.
their hands or not. Right? You have equipment you're paying off. You have things that you're paying for, electricity. So no matter what, you're paying $9,000. Okay. So this is most likely going to increase up to a certain point, and then let's see, should it decrease? Yeah, it probably will at some point. This is also probably only for a certain range of units that you're producing. But let's go ahead, let's find the marginal cost. Marginal cost would be the first derivative. Go ahead and take the first derivative.
So wait, for each item you would add $9,000?
No. If you plugged in 0 and 1 and 2 and 3 and 4, this is going to change, but it's going to be 9,000 plus that amount plus that amount. The 9,000 would be like you're starting out. Like if you produce nothing, it's still $9,000 because you have that overhead. So every month, I helped run a business once. Every month, whether we sold archery equipment or not, we had to pay rent, right? We had to pay workers, we had to pay all this stuff. So whether we made arrows and sold them or not, it still costs us money. That's what this says. It says it's going to cost you money whether you have your equipment sitting there or actually working. Okay? So we'll want to find marginal cost, the cost of producing the next item. Oh, so we're going to have
It's not 2.2. 0.2 times 2 is 0.4, yeah. Jeez, man. Oh, brother. Yeah, I added it. Jeez, man. Try that again. Wait, when did I mess up? All the way, okay, jeez. Negative 0.4x plus 200 equal to 0 to find the peak. Negative 200, no, I don't know why I like doing that. 0.4, x equals 200, so that was 0.4. X equals 200 divided by 0.4. $500.
that. Did you find that as your derivative as well? Okay. Could you find
Or
out
that would
the
be
cost
500
of
items,
producing-
wouldn't it? X is items. So if you plug that in, you find out how much money it would cost. Plug it into the original function.
the 100th item? That would be C prime. What's your cost at the 100th item?
I think of 200.
What was it?
160.
160, okay.
Oh.
Whatever we're talking in
That
$1,000,
would be-
dollars.
yeah,
whatever it is.
160.
It's 160. Do you all get 160? Do 101 for me, okay? How much?
159.6.
Wait a second. Does it seem right to you?
Yeah.
You got to think about what marginal cost means, okay? Marginal cost means, and think about the curve here. The curve goes like this. Marginal cost means the cost of producing the next function or the next item. So this says, the more that at this point I'm producing the next one, this individual one costs me less to produce than that. Maybe that's because I don't know. You get some sort of a break, a price break if you buy a certain amount of equipment, or sometimes you have your workers who are working all day. It's easier for them to produce this amount than a previous amount, but that happens in business a lot. Your cost changes item to item. So this one costs $160 to make. This one only costs $159.6 to make. The next one would be
Okay, I
even
see.
less. Most likely they did 102. Try 150, see what that does.
$140.
You got 140? $140 if you produce for the 150th item. So we keep going, keep going. It might cost us less and less to produce as we keep on going and going and going and going. Let's see, is your slope? Yeah, because your slope is always negative 0.4. Do you see that? So negative 0.4 says we're constantly dropping. So the more we produce, the less it costs us to produce. Now, after a while, that's probably not going to be so great because we're going to outpace our demand for our product. We're going to end up with a glut, which would cause our prices to probably fall. But this is the way that at least you can calculate your marginal utility, the cost of the next item. How many people understood the cost of that? Again, I'm not a business teacher, so I probably can't explain this as well as, well, I could have 10 years ago, firstly, but as well as a business professor either. But I can tell you how marginal cost does work, and that's the way it works. Now, the next thing we get to do, you're going to enjoy this. You ready to enjoy this? Haven't you been having fun today?
Oh, function, trig functions. Yeah,
Say
no.
yes.
That's
We're
actually
gonna
gotta
talk
suck.
about derivatives.
That's a shocker.
Yeah.
So we got derivatives of trig functions, chain rule, implicit differentiation, related rates, and then that's it for chapter 2. Wonder where the integrals come in. Evaluation of definite integrals. Looks like chapter 4.